Okay, let's make another video, this time for 6.3, justifying a claim based on a confidence interval for a population proportion. We're going to start, though, with constructing a confidence interval, and we're going to show you how to do that. We're going to go through the entire process. Let's use an example problem where, let's say, Fred operates a nursery where he plants many thousands of plants every year. He starts vegetable plants to sell every spring. Seeds for pepper plants from his current supplier have a germination rate of approximately 80%. If you don't know what a germination rate is, that means how many of the seeds or what proportion of the seeds you would plant that you would expect to actually sprout and grow into plants. The seeds that you plant and that would actually sprout and grow into plants. So a new supplier offers to supply seeds with a higher germination rate. Now, Fred wants to investigate the new supplier's claim before he signs a contract. So he chose a random sample of 500 seeds from a new supplier, and he planted them, and he's found 412 of them to germinate. So the first thing you notice is that 412 is more than 80% of 500. So it appears that there may be evidence to claim the new supplier's seeds have a higher germination rate. But we need to investigate that. And to do that, we're going to construct a 95% confidence interval to estimate the proportion of seeds from a new supplier that will germinate. Recall what we talked about in the last video. We need to do some things. There were 4 things we had to do. The first one was we were going to name the interval we're going to use. Here, we're going to use, let's just put name the interval. Now you can name it without saying name the interval when you do these, but I'm just going to tell you what we're doing. Okay. We're going to do the name the interval. We're going to call it a 1 proportion z-test because we are calculating a population proportion, or estimating a population proportion based on a single sample. So 1 proportion z-test, or sorry, z-interval. Recall that the formula, oops, I don't have my, so I can get that picture. Let's go back and get that picture so we can have it. We could also put the formula up there. I want to put the formula as many times as I can right now to get that in your head. The first condition that we had to satisfy if we're going to construct a confidence interval for a population proportion, we have to name the interval. And that's what we just did. We named the interval. The next condition we're going to have to meet is we're going to have to check and make sure that the conditions for inference are satisfied. We need to check the conditions for inference. We have a random sample that was given to us in the problem. We are going to check and make sure that n times p hat, sorry, that's going to equal 500, the number of seeds in our sample, times 412 divided by 500. One thing I want you to notice is that when you're doing these word problems like this, your n times p hat is going to be the number of successes in your sample, because the n is the sample size, the n in the denominator here is the sample size. Those are going to cancel and multiply, and we're going to get 412 here, the actual number in your sample. If you put this in the calculator, that will be your x value also. But n times p hat is equal to 412. That's greater than 10. And what you may already see is that n times 1 minus p hat is going to equal 500 times, now it's 1 minus 412 over 500, but that only leaves 88 over 500. That's the number of seeds that didn't germinate in this context. That's 500. That's going to equal 88, the number of seeds that didn't germinate, and that's greater than 10. So our normality condition, the condition that guarantees that we're going to have a sample distribution that's approximately normal, is guaranteed. And the last thing we have to say is that we expect that n is less than 10% of population size. In this case, what I would say to satisfy that condition, I would say we can assume there are more than 500, the new supplier has more than 5,000 seats. Say plant seats, because that's what we're checking. So that's our conditions for inference. We have checked our conditions for inference. We've guaranteed there's a random sample. Our n times p hat and our n times 1 minus p hat were both greater than 10. And our sample size was less than 10% of our population. Now, the next thing we're going to do is perform our calculations. I'm going to name our sea level. I'm going to use up here because we've got so much of this. That is, here we can just reduce the size of the font. I think we can reduce the size of the font. Maybe not. All right. We're going to perform our calculation. Our confidence level, we're going to use a 95% because that's what it said. Our Z star for a 95% confidence level, this is something you really need to know because it's used so much, is 1.96. Our N is 500. And our P hat is, let's go ahead and figure out what 412 divided by 500 is. Oh, let's go over on the calculator then. I forget I got this calculator up here. 412 divided by 500, 0.824. Now, if I plug all that in, I don't have really access to anything that's going to let me do that here. I will tell you though, we've stated all these things. Now we can go to the calculator and we can let it do it. We can plug this in. And I would advise you to plug this into the formula. Let's see, I think I still have that here copied. Yes. So you would plug your p hat in for p hat here and here and here. Do Z star in here and your N here. And then we will give our answer in the form of an interval. I want to show you though how you do this on the calculator. If we go to stat and to test, whoops, forget we're going to use these. And then down to where it says 1 prop Z int. That's a 1 proportion Z interval on the calculator. Hit enter. It's going to ask us for our X. That's our number of successes, our number of in our sample that satisfy the condition. So we're going to do 412. And then we're going down. N was 500. That was our sample size. Our C level, our confidence level is already set at 95%. We're going to go down here and tell it to calculate. It's going to give us an interval that says our interval is between, whoops, let's do 0.79 and 0.857 or 0.85, yeah, 0.857. So our interval is 0.79 to 0.857. Now we've performed our calculations. We've got one more step to do. And that's where we're going to make our conclusion and context. This. And so our conclusion and context is going to say, we are 95% certain or confident, whichever way you say, the true proportion of pepper plant seeds, that's our in context, from the new supplier, have a germination rate, that will germinate, is between 0.79 and 0.857. If we were asked, does this suggest, is this enough evidence to suggest that the new seeds will have a higher germination rate than the old seeds, the former seeds? We would say no, because the 80% from the old supplier is contained within this interval. And we're going to talk now about what makes the interval work, how it works, and why this would not be enough evidence to say that these seeds will have a higher germination rate. But that's how you construct a confidence interval. So let's talk about how confidence intervals work, and let's get back to this and see about this justification thing. Remember the sampling distribution for p hat. It's the distribution of all possible p hats from a sample size n. So if you have 100 possible sample size n, there are 100 possible p hats, and if you calculate all those and put them in one distribution, that would be the sampling distribution for p hat. Each p hat in a sampling distribution, if we take that p hat and add and subtract a margin of error, is associated with a confidence interval. And so there are the same number of possible confidence intervals that there are p hats in our sampling distribution. And so now the probability of selecting a confidence interval that actually contains the true population proportion, this is where the theory of the confidence interval, this is the key to it, all right? When we calculate a 95% confidence interval, we estimate that approximately 95% of all the possible confidence intervals here contain a true population proportion. So the probability that our randomly selected confidence interval, randomly selected sample, results in a confidence interval that actually contains true population proportion is equal to our confidence level. %95 of all p hats are associated with a confidence interval that contains the true population parameter. And we take one single random sample. There's a 95% probability that that sample is a p hat that when we construct a confidence interval around it contains the true population proportion. That's how they work. So let's talk about calculating Z for a C% confidence level. That's important. It's more about how this works. So what we want to think about is the distribution, the sampling distribution for the population proportion. And once we've satisfied those conditions for inference, we know that that distribution is approximately normal. And the mean of the p hats, the sampling distribution for p hat, is equal to the true population proportion p. And we know that the standard deviation for the p hats is equal to the square root of p times 1 minus p over n. We don't know p. We're estimating p. So we are going to use, to estimate our standard deviation, we're going to use p hat as a point estimate for p, for our standard deviation. And that's where we're going to use and construct the margin of error. So what we want when we're constructing this is we want to find in the sampling distribution the Z star, or sorry, not in the sampling distribution, the standard normal distribution, that contains 95% of the data, The middle 95%, this is minus Z star, by the way. And this is no longer, if you recall, what I told you before was that we could convert any normal distribution into a standard normal distribution where the mean is 0 and, well, where did my marker go? I do not know where the marker that I was using went. Oh, nope, that's not it. Size. Let's do that. The mean is 0. This is the Z star. That would make this actually the number of standard deviations times the standard deviation, or Z star times the standard deviation of P hat. Listen, this may seem a little confusing right now. I'm going to redo this. I'm not going to start this video over, so don't say it. The way we're going to get to Z star, is we're going to take the standard normal distribution, and we're going to look for the Z star so that between negative Z star and Z star, 95% of the data lies. And we know that normal distribution is symmetric. And so that tells us that over here is 0.025 and over here is 0.025. And so if we want to find the Z star when we're given an area under the curve, we're looking for all the area to the left, and we're going to say that Z star is equal to the inverse norm, and all the area to the left is going to be the 95% plus the 0.025, so that's going to be 0.975. And then the mean of the standard normal distribution is going to be 0, and the standard deviation is going to be 1. So we're going to type that in our calculator, and we're going to calculate the Z star for this 95% confidence interval, which I've already told you what it is, but I want to see it. You'll have to do this sometimes for other problems. So we're going to go to the inverse norm in the distribution menu, second bars. We're going to do the inverse norm. Hit enter. Oh, this doesn't have what you have on your calculator, but it's going to ask you in your calculator, it's going to look a lot more like this, where it's going to ask you for the area, for the mean, and for the standard deviation. And so here, this is an old operating system. I'm going to put in 0.0975 for the area. I'm going to put in 0 for the mean and 1 for the standard deviation. You'll have a nice pretty thing here. I'm going to hit enter, and it's going to give me 1.95999. That's where our 1.96 comes from. If I wanted to come up with a Z star for a 92% confidence interval, then I would be looking at a normal distribution, mean 0. I would want 92% of my data in here. That would leave 8% for either side, so that would be 0.04 over here. If I wanted to calculate Z star, I would use my area as 0.96. So if I want to do that, I'll go over here and I'll say inverse norm, second distribution, inverse norm. My area would be 0.96 because that's the 0.92 plus 0.04. That's all the area to the left of Z star. Sorry. So I'm going to go over here and type in 0.96 for area. And my mean is 0. My standard deviation is 1. We'll tell it to find. So my Z star for a 92% confidence interval would be 1.75. That's how you calculate the Z star. So your Z stars for your most common area, you can check these on the calculator if you want. But for sea level 95%, we said Z star is equal to 1.96. For sea level, 90%. 90, 95, and 99 are your most common. Your Z star is equal to 1.64. And again, you can construct that and find those. And for a sea level, confidence level of 99%, your Z star is 2.58. You can find all those in the calculator if you want to verify that. We just showed you the calculated Z star for not so common confidence levels. We're going to build that off of the normal distribution. Let's see, there we go. No, there we go. We're going to put the confidence level as the amount inside the middle. And then we're going to figure out the area to the left of that using the symmetry, knowing that all of it's 100. And so, or 1.0, so 0.92 plus 0.04 plus 0.04. That's going to make the area to the left of the Z star 0.96. And we would plug that in for the area into the Z inverse norm. And we use the standard normal to find the Z. And that would give us the 1.75 for 92%. Or it'll give us the 1.96 for the 95%. Or it will give us, like we said over here, 2.58 for 2.58 for 99% and 1.64 for 90%. But you can calculate that for whatever confidence level you want. So now let's talk about the relationship between Z star and the confidence level. To do that, let's look again at the formula. As the confidence level gets larger, the Z star gets larger. Now what that does is that makes the interval wider. Because when Z star gets larger, it multiplies the amount that we're adding, the standard error that we're adding and subtracting from P hat. It makes that larger. So the interval actually gets wider as the confidence level increases. It casts a larger net to capture the true population parameter more often. So as the Z star gets larger, as the confidence level gets larger, and that makes the interval larger. So as the confidence level decreases, the Z star decreases. That makes the standard error times Z star less, and that makes the interval more narrow. A smaller interval will capture the true population parameter fewer times than a larger interval. Let's go back to our simulation again. And this time, let's change our Z to 1.64 for a 90% confidence level. Let's run this and see how often we catch the interval, or we catch the true population parameter. About 90.9% when we ran it 1,000 times, which is pretty close to 90%. We run it again. 90.1%. So the interval is not as wide. It captures the population parameter fewer times. So as the confidence level decreases, Z star decreases, and the confidence interval's width decreases. As the confidence level increases, Z star increases, making the confidence interval larger or wider so that it captures the population parameter more often. The margin of error for a confidence interval is the Z star times square root of P hat times 1 minus P hat divided by N. It's how much we add to and subtract from the P hat. So we got the formula for the interval. The margin of error, is just this part. The Z star times the square root of P hat times 1 minus P hat divided by N is the margin of error. Oops. And I didn't really want that equal sign in there, that little part of the equal. But the z times the p hat times 1 minus p hat times n all on the square root. That's the margin of error. So let's talk about the relationship between the margin of error and sample size. The p hat times 1 minus p hat is fixed once we have the sample. The z star is fixed once we have the confidence level. So as the sample size increases, it makes this fraction smaller, which makes the margin of error smaller. So a larger sample size have smaller margin of errors. Smaller sample sizes have larger margin of error because we're dividing by smaller numbers, making this fraction larger. With the confidence level, again, we talked about this a few minutes ago, it makes z larger when we increase the confidence level. So that makes a larger margin of error. Okay, so larger C levels, confidence levels, have larger margin of error. And smaller C levels have smaller margin of error. Now let's have some fun. Let's talk about calculating a minimum sample size to guarantee a maximum margin of error. To do this, we need to identify the Z star for our desired confidence level, and we need to identify our desired maximum margin of error. So let's say that we were going back to our example, and we wanted to guarantee a margin of error of no more than 2%. So we'll take these numbers. Let's go ahead and do this now. I'm going to move this slide down here. Oops. Duplicate this slide. And I'll move it down here. So I'm going to go here. Let's say we want to limit our margin of error to no more than 2%. So we want a margin of error less than or equal to 0.2. Oops, 0.02. So we're going to set this up. I'm going to go to Paint because I can draw on that. We're going to set this up with our margin of error as 0.02 is going to be less than or equal to, or sorry, greater than or equal to our true margin of error, which is going to be our Z star. If we're doing a 95% confidence interval, we have 1.96 times the square root of, and let's see again what we had. We had 412 divided by, oops, second quit. 412 divided by 500 was 82.4%. So we're going to use 0.824 times 1 minus p hat, which is going to be 0.176, divided by the square root of n. If we're looking for the sample size that will limit our margin of error to 2%, we need to solve this for n. So the first thing I'm going to do is divide both sides by 1.96. And then I'm going to square both sides to get rid of the square root and end up with a 0.824 times 1.176 over n. Now I can multiply both sides by n. And then divide both sides by this huge quantity here, and get my sample size greater than or equal to 0.824 times 0.176 divided by 0.02 over 1.96 squared. That's going to be equal to, when I type in my calculator, so 0.824 times 0.176 divided by, I'm going to put this in parentheses because it's all under the square root, or all under the fraction in the denominator. This is going to be 0.02 divided by 1.96 all squared. That's just the denominator squared, remember that. So this tells me I need, 1,392.81. N has to be greater than or equal to that. So the minimum sample size I could have is 1,393 to guarantee the margin of error to be 0.02 or less. 1,393. We can calculate that minimum sample size with a limit on our margin of error using that method. As the margin of error increases, we'll talk about relationships between the margin of error and the width of the interval. We already did this, I think. But as the margin of error increases, the width of the interval increases. So the width of the interval increases as the margin of error increases. The confidence level, as the margin of error increases, the confidence level also increases. Or let's not look at it like that. Let's look at it like a larger confidence level makes a larger margin of error. A larger sample size makes a smaller margin of error. We've already talked about most of this. And now for the trick, the p-hat. The closer p-hat is to 50%, the larger the margin of error. The farther from 50% p-hat is, the smaller the margin of error. And I'm going to show you why that is. The larger we make this part under the square root, the larger we're going to find, the larger margin of error we're going to have. Because once we set z based on our confidence level, this part here is what's going to get larger or smaller. So I'm going to look at my y equals. I'm going to take what's underneath that square root, and I'm going to call p hat x. And I'm going to multiply that times 1 minus x. And I'm just going to choose a sample size here, whatever sample. Let's do 1393. So, no, let's not do 1393. That's going to make it a little small number. 1 minus x. Since n will be fixed, let's just look at this. If I make this as large as it can be, if I make this as large as it can be, and it has to be between, p hat has to be between 0 and 1. And if I make this p hat times 1 minus p hat as large as it can be, that's going to maximize the margin of error. It's going to be the largest the margin of error can be. So what I'm going to do is I'm going to graph this, but I'm going to graph it in a window where x is 0 because p hat can't be smaller than 0. And x max is 1 because p hat can't be larger than 1. As a matter of fact, the margin of error would be 0 if it was, if p hat was 1. The margin of error would be 0. So we can't even have that. I'm going to look at the window here. I'm going to go ahead and change my y max because I know what's going to happen here. I'm going to change my y min and y max to -5 and 5 to give us a little better view on this. And then I'm going to tell it to graph. As a matter of fact, look how small it is. Let's go ahead and make our y max and y min. Let's make our y min 0. and our y max 1. Oops. Now you might notice that this y equals is a quadratic. If we distribute that, we get x minus x squared, which is a quadratic. It's a parabola, and its vertex is right here. So let's do second trace maximum. And let's do the left, oh, I said first curve. There's no first curve. I must have hit the wrong thing. Let's second quit. Let's do second trace maximum. I must have hit intersect on accident. Left bound, that's what I wanted. So I'm gonna move to the left side of that, hit enter. I'm gonna set my right bound, move to the right side. If you know the calculus, you can take some derivatives instead of equals 0 and find the maximum here. I'm gonna tell it to guess, and you see that x, which is my p hat, is 0.5. So that's where the largest possible margin of error comes, is when p hat is 0.5. As p hat gets closer and closer to 0, you see what's happening. When we graph this, the p hat, or the margin of error, is going to get smaller and smaller and smaller. As p hat gets closer and closer to 1, then the margin of error is going to get smaller and smaller and smaller. So the maximum value for p hat is going to be 0.5. And so when we want to calculate that, we will use 0.5 to maximize our margin of error. What about justifying a claim based on a confidence interval for a population proportion? A confidence interval cannot prove a claim true. What a confidence interval can do is provide evidence to suggest a claim is false. If the claimed population proportion is outside of the interval, then we have evidence to suggest that the true population proportion is either higher or lower, depending on whether the interval is above or below the claimed proportion. So if we have a confidence interval where the lower bound is less than 0.8, then the evidence suggests that a true population proportion is greater than 0.8. If we have a confidence interval where the upper bound is less than 0.8, then we have evidence to suggest that the true population proportion is less than 0.8. If the population proportion is contained within the interval, there's no evidence to prove that the claim is true, but there's insufficient evidence to prove it false. When we go back up to our example and we came up with that proportion, that interval from 0.79 to 0.857, 0.8 is in there, and it's right close to the left endpoint that left the lower bound. Most of the interval is way above 0.8. But as long as 0.8 is anywhere in this interval, there's no evidence to suggest the claim is false. It doesn't matter if 0.8 is on the far left, in the middle, or on the far right, or anywhere in between. If 0.8 is in the interval, there's no evidence to suggest that the claim is false. That's an important concept to understand. So we can't prove a claim true, but we can provide evidence to suggest a claim is false. This is a slide that doesn't belong on this video. That's left over from before. This one doesn't either. That's the end of this video. So thank you. Let me know if you have questions.